Welcome to this presentation on autonomous economic agents as a second layer technology for blockchains. Framework introduction and use case demonstration. This is joint work with Ali, who's on the call, as well as Marco Favorito and Jonathan Ward, colleagues at Fetch AI. If you look at Web3 and distributed ledger technologies, then one of the big benefits they enable us is that they allow for trustless value exchange and public execution of smart contracts. However, there are also clearly identified shortcomings. One of them is that the user experience is fraught with, for example, excessively many steps to execute a task or action, a high difficulty, often due to the complexity in unintuitive processes, and a high risk of error. At the same time, smart contracts are restricted to being reactive. They require transactional contract call. And they are limited in what they can enable. Now, why do we care about these problems? Well, these limitations have negative implications on user adoption, and they prevent DLTs from being general purpose. We propose a solution in the form of autonomous economic agent, AEA technology. These are software agents that act autonomously and pursue an economic goal. Thereby, they complement the existing DLTs as a second layer technology. And we realize this technology in a framework that enables modular development. What are the implications of this? Well, AEAs help address a number of problems. They simplify and reduce the complexity in the user experience through automation. They can help move complex decision-making and machine learning capabilities in a modularized and reusable way off-chain. They also allow for proactiveness, thereby allowing for an agency layer to exist on top of the smart contract functionality provided by DLTs. We will structure the remaining presentation as follows. I will introduce the autonomous economic agent framework in more detail. I will then hand over to my colleague Ali, who will discuss an AEA use case, the trading agent competition, and he will conclude by reverting back to our introduction. So let's first discuss the autonomous economic agent, short AEA framework. There's a number of headlines I would like you to take away. So firstly, we think it is a way to easily and quickly compose software that creates economic value. One way to think about it is like a web framework for agents. Although our first implementation is in Python, in general, everything we build in terms of protocols is language agnostic and open source. The framework is currently developed by my team at Fetch AI, but packages and extensions are already developed by our community of developers. Let me describe a number of characteristics of the AEA framework and the environment in which it resides. Well, AEAs are residing in a multi-agent environment, which means there's multiple stakeholders who interact in a potentially adversarial environment. The agents therefore should be designed such that they communicate via messages and in an asynchronous way. They communicate in an asynchronous way. We also have a number of system requirements. For example, agents need to be able to search and discover each other and have a requirement for financial settlement and smart contract execution as provided by decentralized ledger technology. So this picture on the right-hand side or illustration highlights the main system components. AEAs might be directly or indirectly connected with each other. They might or might not connect to multiple ledgers, and they need to be able to have access to a search and discovery system. The AEA framework itself has multiple components. The AEA packages are extendable by the community, and they consist of 4 types of packages: connections, protocols, skills, and contracts. I will take you through each of them in turn. At the same time, we have a number of core objects provided by the framework. These include, amongst others, the wallet, the decision maker, and the multiplexer, which we'll discuss in due course as well. Let us first look at the protocols, one of the AEA packages. A protocol defines agent-to-agent interactions. As such, it needs to define the messages and the permitted payloads, the logic, how we decode and encode these messages for transport, and optionally, it can define dialogues, which essentially provide a set of rules over the sequence of messages. If a developer wants to incorporate a new interaction, they can do so by defining a protocol and generating it. On the right-hand side, what we see is a simple illustration of the concept of a protocol here, the message, which is wrapped by an envelope, similar to how we deal with it in a physical mail system. Let's next look at the connections. Connections wrap SDKs or APIs and provide the interface to the network, other ledgers, or other services, potentially even in process. Sometimes they also need to translate between the internal message-based agent-to-agent language and external languages or protocols. We allow you to run multiple connections at the same time in a multiplexer. And here on the right-hand side, we see an illustration of this concept where we have a peer-to-peer connection, which allows for agent-to-agent communication via protocols. We have a HTTP connection, which accepts request response cycle in HTTP protocol. We have a ledger API to communicate with a ledger, and we have a search API to communicate with a search system. Next, we'll look at the skills. Skills implement the business logic to deliver economic value. From the perspective of the framework, they're like black boxes. They're horizontally arranged, meaning that individual skills don't interact with each other much. Skills can be very simple in the sense that they can implement if this then that logic, or arbitrarily complex. For example, they could implement a deep learning model. There are 2 core abstractions which are important with respect to skills. One is the handler, which provides the reactiveness of the agent. It deals with the incoming messages. So here on the right-hand side, this is illustrated by a message being consumed by a handler and then potentially, though not necessarily, resulting in an outgoing message. We also have behaviors. They provide the proactive element of the AEA. One way to think about them is that they initiate often a next action to further the agent's goal. They could be cyclic, one-shot, finite state machine, you name it. The framework calls certain endpoints, which then result in potentially new messages being generated by the behavior. The next and final package we will look at are the contracts. Contracts are containers for smart contract bytecode and ABI. Their responsibility is to expose a consistent API to abstract the implementation specifics of the ABI from the skills. So usually what they would do is implement the logic to create and deploy a contract, for instance, send transactions or construct transactions, make contract calls. Now, having covered the 4 packages, we come to one of the internal or some of the internal components of an AEA. The most crucial ones are the wallet and the decision maker. Because AEAs are meant to generate economic value, they require a wallet, which holds the private and public key pairs, referencing some assets on a chain, say. Now, it would be problematic from an object capabilities point of view to expose the wallet directly to the skills. Instead, what we do is we only expose the wallet to the decision maker, and the skills have to propose transactions to the decision maker, which then decides whether to perform or not perform these actions. The decision maker therefore needs to have a representation of the preferences in the space in which it is active, the AEA is active. It needs a representation of ownership states and of goals. You can think of the decision maker as the crypto-economic brain of the AEA. Let's put it all together. So we have envelopes, which are the wrapping the messages, which are the means of communication of the agent. These are exposed to the externals of the AEA via the connections run in a multiplexer. We have the main loop, which is responsible for calling the endpoints on the skills and the decision maker, handling all the internal messages. And we have the contracts to interact with ledgers. So I would like to quickly summarize what we just saw. The objective here is to build or provide a framework which lets you easily and quickly compose software that creates economic value. We want to bridge the Web 2 and the Web 3. And we believe that merging the concepts of distributed ledger technologies and AEAs will allow us to build open multi-agent systems which can be deployed in the real world. At this point, I will hand over to my colleague, Ali.
Thank you, David. So at this point, I would like to talk about an application of the framework, which we call the trading agent competition. And we think that this is a relevant application, and hopefully through this, some of the contributions of the framework, which David has mentioned, can be sort of exemplified and highlighted. So the setup of the competition is as follows. We have a bunch of agents who would like to compete with one another. The package that we have already comes with two types of agents, one baseline and another one model-based. The baseline is a simpler agent in construction and strategy, and the model-based agents, they use a form of reinforcement learning to construct their strategies and come up with actions. There's also a unique controller agent that has to be in every competition and that manages and maintains the state of the competition. Now, in the competition, there are sets of instances of goods of differing types. We can see here, and there's also another type of good which we call money, and this is used for as a medium of exchange. All of these different good types and the money type, they are represented as fungible tokens in an ERC 1155 smart contract. Agents are given endowments in good types, in goods and money at the beginning of a round in a competition. And this is basically a subset of the goods and money that each agent is assigned. Crucially, also, agents have preferences over these goods, and this is defined by a utility parameter that agents get at the beginning of a round, and it allows them to rank sets of combinations of good and money, and allows them to sort of decide how to proceed in the competition. Of course, because the competition uses blockchain, there is a cost associated with every transaction, and so we do explicitly represent that as a trade cost. There are three phases to the competition. There is a pre-trading phase, during which agents who want to participate in the competition, they register with the controller, and the controller also sets up the competition in the terms of deploying the smart contract, minting tokens, etc. If a minimum number of agents do register with the controller agent, only then the competition moves forward to the next stage. Now, the next stage is trading stage, where it consists of a number of rounds with pauses in between. Now, at every round of the trading phase, the controller first generates preferences and endowments for every agent. It then sends the details of these as well as the address of the contract to the participating agents. So then they can actually make the trades. The agents then engage in trades with one another. They can register their services, the service that they provide on a registry. And by that, we mean an agent can say basically that I'm a buyer of a certain good or I'm a seller of a certain good, and they can register it in that sort of discovery node. And other agents can search for services, basically searching for buyers or sellers of good in that registry, and they can find each other. They can communicate with one another over a network of relay nodes over the internet. And once they finish with a round, at the end of a round, the competition, the controller agent constructs a league table for that round, ranking the agents based on their performances in that round. Once all the rounds are completed, we move to a post-trading phase in which the controller constructs a final league table by averaging across all league tables of the rounds. Now, when it comes to strategy in this competition, and if you want to enter an agent in the competition, there are two dimensions that you have to think about. One is finding the best trading partner as an agent, and the next is doing the best kind of trade with them in terms of pricing. In TAC, specifically with the agents that we have by default in the package, the agents simultaneously buy and sell in the sense of being able to buy goods and sell goods, and it's not the case that some agents can only buy or some agents can only sell. They use the utility metric that they have in order to compare the different states and to decide whether to go ahead with the trade or not. And the baseline agent is the simplest type of agent in construction. They simply decide that based on a positive marginal utility. So if there is a positive marginal utility, they would go ahead with a trade. Now, once the agents actually find each other and they decide that they want to sort of see if they want to, engage in an action that results in a transaction, they start a negotiation process. The negotiation itself is designed as a protocol within the framework. So it is another type of interactions that we've designed ourselves. It is inspired by the FIPA language, for those who are familiar, and it defines the type of messages that agents can send to one another and how they reply how they can reply to each message. So an example of a negotiation is the following, where you start with a CFP, a call for proposal for an offer. Then you receive a proposal involving an offer and a price. You accept that proposal and you get a matching accept from the other agent, and this is a successful negotiation. You can also start your negotiation dialogue with a CFP, with a call for proposal, and the other agent can just decline, where he doesn't even want to start a negotiation. Or you can start the negotiation again, get the proposal, get an accept, but get a decline after that because the other agent doesn't think that he wants to continue the negotiation anymore for whatever reason. I think it's useful to have a look at a demo at this point. Now, bear in mind that this demo is using an older version of the code that we have in the framework, and that the transactions here are not actually stored in a blockchain, but is sort of stored in an emulated DLT. So this is the window that we see of the agents. There are 10 agents, 5 baseline and 5 model based. And you can see as the number of transactions is increasing, you can see the increase in their score of all the agents. Now, we have run the competition a number of times ourselves, and we have also run it physically, inviting developers. And this is some of the analysis that we've got out of these runs. In all the runs, we have 10 agents, 5 baseline and 5 model-based. There had been 103 runs with different seeds at the beginning. And what we measured is, amongst other things, is the difference between the final score of an agent with its initial score relative to this theoretical equilibrium. And this latter part is to make sure that the randomness of the preferences and the endowments do not affect the overall results. And so you can see the histogram of this on the right-hand side, and we can clearly see the orange lines show the final scores, less the equilibrium, the theoretical equilibrium, and the blue lines are the initial scores, again, less the theoretical equilibrium. And we can see the clear divide between them. This is a statistically and economically gain for all the agents on average. Something else that might be interesting to know is that these agents, they do meaningful transactions because of the success in the scores and the increase in the scores. And they do almost 1 transaction every 15 seconds during the span of the competition in terms of the speed. Now, let's back away again and have a look at the contributions that we mentioned at the beginning of the presentation. So we mentioned a number of shortcomings for distributed ledger technologies. One of them was a problematic user experience that we have. It is often very complex and confusing for humans to interact with these technologies. There are usually many steps involved, and this is especially magnified because of the high-risk environment that DLTs are usually in. And in TAC, we can see that the automation that the framework offers sort of tackles this problem. And in TAC, we can actually see that agents do well in such an environment, while the environment is actually high risk, just as we mentioned, but also much larger in scale in terms of number of transactions and time than typical interactions that humans have with blockchain. It's actually also more difficult, arguably, because of the parallel negotiations that's going on, all the interdependence of transactions, and also the adversarial nature of the competition. We also mentioned that smart contract are purely reactive, and so that sort of limits their scope of what kind of applications you can run and write with them. And so the framework for that offers this sort of proactive layer of agency. And in fact, if we look at TAC, some of the elements of TAC, like search, discovery, and advertisements, none of that can actually be implemented using a purely smart contract setup. We also mentioned that the DLTs might be inefficient for some applications, especially when they get too complex. Things like machine learning. It's been shown by others that machine learning may not be a suitable application to be run on blockchains. It's going to be too costly to store all of that information. And in fact, if you look at TAC, we also have a lot of transient information, like the states of negotiation, which we do not really want to store on a blockchain. And so the framework offers this combination of on-chain and off-chain environment where you can have the values and the benefits of both, having all the transient information in an off-chain environment and storing all the permanent information on the blockchain. Of course, the fourth one is a complex environment for development if you only rely on DLTs and smart contracts, which the framework sort of offers all of these layers of abstractions, and the modularisation eases the development workflow and allows for us to have extendable packages and a reuse of code. So if we have a look again at what we talked about in this presentation, we introduced the AEA framework as a complementary technology for DLTs, which sort of sits on top of DLTs as a second layer technology. They do increase accessibility They reduce complexity both in development and usage. They offer layers of abstraction and modularization, which then increases the reusability of code. And also they sort of provide this missing proactiveness component to purely reactive smart contract setups. And then hopefully you've seen these values and sort of contributions through this relevant applications, which is the trading agent competition. So I hope that you've enjoyed this talk. You can get in touch with us. There is a link to the framework. The framework is now open source and is ready to use. There's a link to documentation to the framework and also to the package, the TAC package, and the TAC skill that I talked about. And if you have an agent that you want to start using, you can sort of get it connected with other agents using that link, agent multi-address. I would like to thank you for listening to this talk and thank my colleague for their work in this on this study.
Thank you as well.